I am Anil Kumar. Welcome to another interesting video on vectors. We are going to consider dot and cross product applications. Scalar projection, vector projection, direction cosines, area of triangle, and volume of parallelepiped will be discussed in this video with my student Akshit. You can always join my classes by sending an email on the address given. Let us now enjoy the journey of success. Hi Akshit, how are you doing?
Yes, sir, I'm doing well. How are you?
Very good, very good. So today, what do you want to learn?
Sir, today I was hoping we can discuss vector and scalar projections along with direction cosines.
Oh, sure, well. Okay, so you're done dot product, right?
Right, yeah.
So it is very much related with dot product. Let me just share with you a whiteboard and then we'll discuss, okay?
Yeah.
So let us say we have two vectors A and B. In that case, tell me, what is A dot B equals to?
So it would be the magnitude of A times the magnitude of B times the cosine between those two vectors, cos theta.
So what you're trying to say here is that if I am given two vectors A and B, let us put B along this side. Let's say this is vector B. And then we have a vector A. Let us say this is vector A for us.
Yeah.
And the angle between them is given to us as theta. In that case, whenever you are seeing angle between vectors, you have to put them tail to tail. You get the idea? Always
Yes,
put
sir.
tail to tail. So now, A dot B is magnitude of A times magnitude of B, that's cos theta. And you can very see it is a scalar quantity, right?
Right.
Since magnitudes are scalar and cosine theta is also a scalar quantity.
Scalar.
Now, you are interested in finding projection of vector, right? So we have scalar
Right.
projection. And we also have vector projection. Literally, projection means that projection of A on B will be this.
Right.
From here. Right? That is what this projection is. You get the idea?
Yes, sir.
So let me write down the points so that it becomes easy for us to communicate. Let's say this is O, this is point A, and this is point B. Then the projection of OA on OB or vector B is, let us say, OP. You see, about a sun or a light source, and right there on the top, in that case, where will this reflection fall on the line? That is how projected. You see the projection.
Yeah.
Little, it means this. So when we say that we want to calculate projection of A on B, it means we want to know what is the magnitude of OP.
OP. Yeah.
Because OP is scalar projection of A on B.
B.
We also write this as A projection on B. Is that clear to you?
Yeah.
If it is scalar projection, we'll write magnitude. We are only interested in magnitude. Now, you know a bit of trigonometry, remember, right? So,
yes, sir.
Trigonometry, what is OP? We know what is cos theta. Cos theta is OP over OA, right?
Right. And OA is just vector A.
Correct?
Yeah.
So OP over OA is vector A magnitude. Is that clear to you?
Yes, sir.
So basically, from here we know that OP is basically equal to the magnitude we are interested in is equal to magnitude of vector A times cos theta.
Right.
That is scalar projection of A on B. Make sense?
Yes, sir. Makes sense.
Now, if you relate to the dot product, you see A cos theta. Let's rearrange this formula. So we could write this as magnitude of B times magnitude of A cos theta, correct?
Correct.
So scalar projection is this part, A cos
Yeah.
theta. So I could write from here that magnitude of A cos theta is basically equal to A dot B over
Magnitude of B.
Does make sense?
Yes, sir. Makes
So
sense.
that becomes a formula using dot product. So
Got
if given two vectors A and B, then find the dot product and divide by the magnitude of B to get the projection of A on B. Is that clear to you?
Sir, so now if it was the projection of B on A, then we would divide by the magnitude of A, right?
Correct. So if let us interchange, so magnitude of, projection of B on A, right?
Right.
Will be A dot B or B dot A is same thing, correct? Dot product.
Yeah, same thing.
Divide by the magnitude of A. Better to write magnitude of dot product divided by magnitude of B. Is that okay? Oh, sorry, divided by
Magnitude of A.
So if it is a projection on A, so it'll be like this, right? This you
Yeah.
can extend, and then that will be the projection. You get the idea.
Yes, sir.
So that B dash, OB dash is the projection of B on A. Clearly, from this diagram, you can see they're not the same, right?
They're not the same. Right.
Oh, very interesting question. I'll try to confuse you a bit to ask the question. Okay, so the formula for projection of A on B is right there. Is that okay?
Yeah.
Now tell me, if projection of A on 2B will be how much? Projection of A on 2B, twice B, will be how much?
Sir, so since the 2B is just a scalar quantity multiplied to the vector B, right?
Yeah.
Then would we just add the 2 wherever the B goes before
Okay.
the B?
Yeah, you can do that. Yes.
So then in that case, would it be A dot 2B over magnitude of 2B?
Correct.
So that would be your answer, right?
But 2 and 2 will cancel, you get the same answer, right?
Right, right.
So what you said just now is very good. A times 2B, right? And this is 2B magnitude, right? So magnitude is a scalar number, 2 and 2 will cancel. So ultimately you get A dot B over B, right?
Right.
You see, if B is longer, how does it matter? My projection is this only.
It's still the same. Yeah.
So it is independent of the vector B.
Right.
It is only dependent on the angle between the two. You get the
right.
If B is half, it doesn't matter. I'll draw a dotted line. The projection is going to remain as
yeah.
You get the idea?
Yes, sir.
Very important concept.
Right.
So scalar projection absolutely clear?
Yes, sir. Absolutely clear.
Okay. So let's remove this and figure out if vector position can be derived. We'll go with the same diagram.
Yeah.
So we're saying one vector B is here. You've seen it could be of any length, doesn't really matter.
Yeah.
What matters is the magnitude A and the angle between the two. This is what it matters. Because the projection, as you've seen, is that projection.
Yeah.
Now, we have already figured out that scalar projection is what? Let's write scalar projection first. Dot product of A and B divided by magnitude of B. Easy.
Right.
When I say vector projection, I'm actually saying that I also want the direction in which the projection is. It is along B direction, right? It is along the direction of B, right?
Right.
That means direction is what? Direction is same as
Vector B.
direction as B, right? So if
Yeah.
I add this direction to it, then we get the vector projection. So what is
Right.
the direction along B? We can say unit vector along B, right? So unit vector along B will give me the direction. Magnitude is what?
Right.
So the vector projection will be what? Tell me.
So in
Times
over magnitude of B.
times direction of B. Unit vector will be the
B
vector
over magnitude of B.
over magnitude of B. Is that clear to you?
Yes, sir.
Because this is your unit vector.
Right.
So that gives you the direction. Perfect.
Yeah.
Okay. So that is how you're going to find the direction of this particular vector. Is that clear to you?
Yes, sir. Clear.
Now, can you rearrange and write it in? So it is basically we have A dot B times B over this
magnitude of B squared.
Right? So
yes, sir.
basically scalar multiple of B divided by B square. Is that okay? This is not a dot product. It is like product. You understand? This is not
it's a product.
This is not
Yeah.
right like this. It is not a dot product. You have it's a scalar multiple. So when you find the dot product, you have a scalar quantity, right?
Yeah.
And scalar projection gives you scalar, and then you're multiplying scalar with a unit vector along B. Is it okay?
Yeah.
So what is B square? B square is B dot B, right?
Right.
So you could also write this as V dot B, right?
Yes, sir.
So A dot B over B. So B dot B will be B square. Is it okay?
Yeah.
Times vector. So that becomes the vector projection of A on B, correct?
Correct.
So that is what scalar and vector projection is. So I hope this concept is clear. We can now take some examples, okay?
Yeah.
Let me just write down one example for you, and let's figure out the answer. Let's say vector A is, let's say 1, 2.
Yeah.
And vector B is, let's say 3, 0, 1. Right?
Yeah.
Okay, if I give 1, 2, 3, 3, 0. Okay. Now, can you find the vector projection? Let's find first scalar projection of A and B. How much?
Yes, sir. So it would be A dot B over magnitude of B, right?
Yes.
So our A dot B would be 4 plus 2 plus 3, which would be 9.
A dot B, right?
Yeah.
Magnitude of B is
3 squared plus 0 squared plus 1 and square root.
okay. So this is how much? 3 plus 0 plus 3. Right?
Okay, yeah, so 6.
So this is 9 plus 1, 10.
Square root 10.
6 over square root 10, right?
Right.
So that is how you're going to find the
Scalar
projection. And to find the vector projection, we have to find unit vector B, right? Is it okay?
Yeah.
Unit vector will be this vector 3, 0, 1 divided by the magnitude, which is square root 10.
Root of 10.
Is that clear?
Yeah. Yes,
so
sir.
3 over square root 10, 0, 1 over square root 10. Is that clear to you? So,
yes.
you got that scalar multiple times this vector. You get your answer.
Right. So you write them together, right?
Yeah. Equals to 6 over square root 10 times, this is scalar multiple, okay?
Yeah.
Square root 10, 0, 1 over square root 10, correct? Now you can 18 over 10.
0.
6
over 10.
You can simplify and write down. but that becomes your vector. Do you see that vector now?
Yes, sir.
This is the vector projection of A on B. Perfect. So that is
Perfect.
what this whole chapter is. It's
Yeah.
a very good application of dot product.
Yeah.
Now, in case the two vectors are orthogonal, then what will be the projection?
So if they're perpendicular,
Yeah.
so then, sir, the projection will be 0, right?
Yes.
Yeah.
The scalar projection will be 0.
Right.
The vector will be 0 vector. You get the idea.
0 vector. Yeah.
So the projection of I on J will be 0. J on K,
Right.
I, J, K are unit vectors which are all orthogonal to one another. Okay?
Yeah.
So that is how we have to approach this question, and this figure in mind helps you to understand many concepts, right? Projection
Yeah.
is cos theta. That is how it is. Okay. So
Yes, sir.
is everything clear to you?
Yes, sir. Everything's clear.
Okay. You said cosine, direction cosine, right?
Yeah. Direction cosine.
So direction cosines, what we do actually is that we try to give direction with the help of reference axis.
Yeah.
So in 3D, you have ijk, xyz, right?
Yeah.
Unit vectors ijk.
Right.
Any vector which is drawn, let's say anywhere in the space, will form some angle with this axis, right? So
Right.
like
Right.
y-axis, this is with x-axis, this is with z-axis.
Z-axis.
You could see angle clockwise or counterclockwise.
Yeah.
Remember, counterclockwise is treated as positive.
Right.
Now, let's derive a formula to find the angle between the vector. Let's say this is vector A. So let me redraw this. Let me draw a vector A here. Okay.
Yeah.
Now, with the y-axis, it is easier to calculate because it looks very similar, right? Horizontal.
Yeah.
The angle it makes is beta.
Okay.
With alpha with x-axis, beta in general with y-axis, and
Yeah.
gamma with
Z-axis.
So clearly, you can see that if I want to find the direction only, we're considering unit vectors. Right?
Yeah.
Then the angle could be found using the
Cosine ratio.
cosine ratio. You get the dot product.
Yeah.
Dot product. So A dot I J in this case. So
Yes.
vector A can be written as A1, A2, A3.
Right.
3 components, right? So that
Right.
gives the vector A ijk, right? Dot with this y, right? So it
Yeah.
is
0, 1, 0.
0, 1. Right? So you know dot
Yeah.
product, angle between them and their magnitude, right? So this is equal to
Right.
magnitude of vector A times magnitude of 1, correct? Times
Right.
cos of angle between them, which is beta. Is it okay?
Beta. Yeah.
So clearly, cos of beta is basically equal to dot product of A with y, right?
Right.
E dot j, right? You can
Yeah.
say you can write like that, and divide by the magnitude of it. Is that clear to you?
Yes, sir. Clear.
So that is how you find the projection cosine angles with
For beta, right?
for beta. So similarly, when you do for then this dot product will be with j. So that means dot product will give you a2, right?
Right.
So it will be like a2 over magnitude of a. Is that clear?
Yeah.
Cos of beta.
And then, sir, to find beta, you just do cos inverse of A2 over magnitude of beta.
Yeah, beta even. So cos
Yeah.
of alpha on similar grounds will be a1 over magnitude
Over
of
magnitude of beta.
and cos of gamma will be
A3.
3 over magnitude of A, correct?
Correct.
Very clear. Now,
Yes, sir.
what is cos of alpha plus beta plus gamma equals to?
So would it be 1?
Square of this.
1, right?
Very important identity. Okay.
Okay.
So when you do that, A1 square plus A2 square plus A3 square, right? Over magnitude. Right? Correct. So magnitude of A is A1 square root, the same thing, correct?
Yeah.
Which is equal to
1.
Because what is magnitude of A? Magnitude of A you can write as A2 over square root of A1 square plus A2 square.
A2 squared plus A3.
You get the idea.
Yeah.
So that is how you find the angle which a vector makes with any axis, x, y, or z.
Yeah.
They are called cosines, direction cosines. So
Yeah.
what we learned here is that clear to you?
Yes, sir. Clear.
So again, this is also a very important application of dot product. So in the dot product application, we learn about the projection, scalar and vector, direction cosines. Also, a very important formula, which is work done.
Yeah.
So work done is also a scalar quantity, and you will be learning about work done using dot product. Is that okay?
Yes, sir.
So we are going to end this session here, but I'd like you to now summarize the learnings, and then you can take some questions from your book, and we will solve these questions based on whatever we have learned. Is it okay?
Yes, sir.
Can you summarize what did you learn today?
Yes, sir. So today we touched upon the vector and scalar projections along with the direction cosines, right? So initially when I looked in my textbook, the formula was a bit scary because it said like a lot of angles, right? Alpha, beta, gamma is equal to 1 and everything. So I didn't quite understand what it was saying, but like upon seeing your way of doing it, I think I can approach the problems with much more confidence.
Right. So it is basically dot product application. If you want to
Yes.
find the projection, the cosine with the x-axis, then because dot product will give you a1 value, right? The other
Yeah.
will divide by the
Right.
magnitude of vector A. We are only
Right.
fixing the angle, and that is it. And so cos of that alpha is there. Alpha is cos inverse of this simple thing, right? Okay.
Yeah.
So now you can take some questions from your book, and let's see if you can answer them.
Yes, sir. I'll just share the screen.
Yes, share, please.
You can see, right, sir?
Yes, I can.
Okay. Okay. We can start here.
Anyway, any question. Take any question.
Yeah.
Okay, question 7.
Yeah. For each of the following, determine the scalar and vector projections of x on y. Okay, so we just do the formula, right? X dot y over magnitude of y.
Correct. That is it.
For each of them.
For each one. Correct.
And then 8, determine the scalar and vector projections of A on each of the 3 axes.
Each of the 3 axes, right? So,
right.
When you take axis, so x-axis will be 1, 0, 0, right?
1, 0, 0, and then 0, 1, 0, 0, 0.
0, 1, 0.
Yeah.
Correct.
And then given the vector A, show with a diagram that the vector projection of A on A is A, and that the scalar projection of A on A is magnitude. So, sir, this is what we did, right?
Correct.
Yeah.
So, given the vector A, show with diagram that vector projection of A on A is A.
Yes.
And that the scalar projection of A on A is magnitude of, right? Because it is the same thing.
Right. Yeah.
Itself means the same thing.
Right.
And cos theta 0. So cos theta 0 means 1.
Right.
Cos of 0 is 1. And therefore you get the same thing, right?
Correct.
Next question.
Yes. Using a diagram, show that the vector projection of minus A on A is minus A.
You can do all.
Yeah. find the scalar and vector projections of AB along each of the axes if A has coordinates that and B has coordinates that. Okay, so this is similar to the question. In the diagram shown.
Go to question number 15, direction cosines.
Yeah, okay.
Because those are straight questions, right? Just do
Right.
the product, magnitude, get the answer. Perfect.
Right.
B, let's see this. Yeah.
So 15. If alpha, beta, and gamma represent the direction angles for vector OP, prove that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1.
We just did it, right?
Yeah, we just did. Yeah.
Right. That's it. Go to 17.
Yes, sir. If alpha, beta, and gamma represent the direction angles for vector OP, prove that sine squared alpha plus sine squared beta plus sine squared gamma is equal to 2.
How will you do it?
So, sir, initially I draw the same diagram we drew, right? With each of the direction cosines, but instead of cosine, you would use the sine ratio in this case, right?
So sine square alpha is 1 minus cos square alpha, right?
Right. So you would use that identity.
So just replace it with 1 minus cos square alpha. What do you get? Just do it.
Yeah.
You should get your result right. So we get 1 minus cos square alpha plus 1 minus cos square beta plus 1 minus cos square gamma. That is my left hand side, correct?
Correct.
So 1, 1, 1 is 3, right? 3 minus,
Right.
in bracket you have got cos square alpha plus cos square beta plus
Yeah.
cos square gamma, right? And that is
Right.
right, 3 minus 1 and you get 2.
Right. Yeah.
That's it. So we've done the whole exercise, no problem, correct?
Yeah.
It's so simple as that. Perfect. So that is
Yeah.
how you should be working on vector projection, scalar projection, and the direction projection. Very simple. I hope
Yeah.
the answer is absolutely clear. So
Yes,
next
sir.
chapter is cross product of two vectors, which we did last time, right?
Yes, sir. We did the cross product last time.
Okay. Let's go to the review exercise.
Okay.
Yeah, let's do some questions from here. Correct.
Yeah.
Now, okay. So just go through this. Do you understand question 1? Can you answer?
Yes, sir. 3 vectors, and then you determine.
Simple knowledge based question, no problem, right? Move on.
Yeah.
Okay. Determine the area of triangle ABC. Go back. Question number 10. Yeah, read.
Yeah. Number 10. A triangle has vertices A 2, 3, 7, B 0, negative 3, 4, and C 5, 2, negative 4. Determine the largest angle in the triangle.
How will you do this?
So, sorry. To determine the largest angle in the triangle, it would be the one opposite to the largest side, right?
Correct.
The largest magnitude. So then I would find the magnitudes and then find that angle using cosine law.
Correct. Now, part B. You're right. Part B. Determine the area of triangle ABC. How will you find area of triangle ABC? Okay. So we will look into some very interesting cases. One is scalar triple product. Let me teach you that.
Okay, sir.
Scalar triple product. Okay.
Yeah.
So that will give you area volume questions analysis. So
Yeah.
scalar triple product is a scalar quantity, right? So let's get back to our exercise whiteboard, and then we'll talk about this concept. And this is called scalar triple product. So what we want to do is we want to do A cross B dot C.
Yeah.
Can you do A cross B dot C?
Sir, so because B dot C gives us a scalar, right?
Okay.
And then A is a vector, so a vector times a scalar, that's not possible, right?
Well, you can do this first, right?
All right, you can do this first, yeah.
Then vector dot vector is possible, correct?
It's possible, correct. So you have to do the cross product first, right?
You have to do the cross product first and then the dot product. Is that
clear? Yes, sir.
Now let's look into your example.
Yeah.
So what you're trying to do is you have this Actually, I'll not get there directly. I'll go indirectly. Let's see how do we find scalar triple product. So let me take up an example from my videos and then we go. Okay.
Yeah.
As we understand, if I have scalar triple product, it means A cross B dot C. So you
Right.
have to always do the cross product first because you get a vector.
Yeah.
And then vector dot vector product is possible. So
It's
never
possible.
dot product first, right?
Yeah.
A scalar triple product actually gives you volume for a 3D shape.
Oh, okay.
When you do A cross B, let's say these are the two vectors on a piece of on your table, for example. Correct? So
Yeah.
this two vector will give you a vertical vector which is perpendicular to them, right? So
Right.
we have a prism, for example, right?
Yeah.
So let me just explain you the concept before we get into. Let's say we have three vectors, right?
Yeah.
Let's say some vector, right? So as soon as I do cross product between these two, what do I get? I get the third product, which is orthogonal, perpendicular. You get the idea?
Right.
Which is perpendicular. So in a prism, let's say if I have a prism, this actually gives me the height.
The cross product gives us the height. Yeah.
Correct? And then
Correct.
and also the magnitude we have got because of the cross product magnitude we got. So that multiplied by this gives me the volume, area of the base. Because when I do the dot product with this, I get the volume of the whole.
Yeah.
So in this question, can you please read the question?
Yes, sir. Find volume of parallel pipe defined by vectors u 8, -3, 4, v -2, 9, 1, and w 0, -4, and -7.
So to find the volume of a parallelepiped, if you are given the three vectors A, B, and C, in that case, what do you need to do? You can do cross product of any two. Let's say you cross
Yeah.
and then do the dot product.
Dot w. So, sir, I can pick any two vectors, right, for the cross
Yeah,
product?
you get the same one. Yeah, any two vectors.
Okay. Yeah.
So you have multiplied length, width, and height distance. You get the idea.
Yeah. Yeah.
And the parallel, we want the shortest distance. So perpendicular distance will be the shortest distance.
Right. Right.
Now, I'm going to show you a technique of doing the three together. Because
Oh,
normally,
okay.
what you will do is you do the cross product first, get your answer right,
Yeah. And then do the dot product.
then do the dot product. What we are doing to do the matrix method.
Okay.
So we'll write u, which is 8 minus 3 and 4. We'll write v, which is minus 2, 9 and 1.
9, 1.
Then we write this 0, minus 4 and minus 7. Do you see that?
Yeah.
Last time when cross product, I showed you how do we find the value of this, right?
Yeah.
Here, when we are doing cross product, we write ijk, right?
Right.
But instead of ijk, I've written the vector u, which is 8 minus 3 and 4.
And 4.
8 times, within bracket, 9 times minus 7, 63,
Yeah.
minus 63, minus 4 times 1, which is plus 4, right?
Yeah.
Minus, alternate plus and minus, right?
Right.
Minus 3 times, so it becomes plus 3. 2 minus this 14, minus 0, correct? Plus 4 times, 2 times 4, both negative makes it positive, minus 0. Do you see that? That is your answer.
Yes, sir.
So straight away, using my matrix method, which I taught you, basic concept, how do you use
Yeah.
it for cross product? You can use it for scalar triple product. Get your answer. You see how fast we got the answer? That's the
Yes,
volume.
sir.
So individually, you do not have to do the cross product and the dot product. That is why I taught you this method. It
Sir,
is
a quick question.
yeah.
So, for example, for the first step, right, when we got 8 times -63 plus 4, so if we're covering up that section, right, what would be our determinant in that
This
case?
is the whole. This is 3 by 3 determinant. So we are evaluating
Oh,
3 by 3
okay,
determinant.
okay.
So 8 times this determinant. Do you see that?
Yeah, yeah. Okay.
And then minus 3 times this determinant, this and this. So leave that row and column, multiply
Yeah.
this. That is the concept. When you go for 4, leave this, and that is your determinant. Is that clear to you?
Yes, sir.
That is how you do it. You
Got
get
it.
so
And then you have to alternate signs, right?
alternate signs. So let me just show you the solution. You got the concept?
Yes, sir. I got the concept.
So this is how we have shown it. Is that clear to you?
Yeah.
So the volume V is U vector times cross product with V dot product, and you wrote, well, as you said, we could rearrange. You see, it doesn't really
Yeah.
matter which vector we write first, right?
Right.
So in this way, I changed the order. I wrote 0, minus 4, minus 7 first, and then the other two, right? So
Right.
you multiply and get your, you'll get the same answer. Is that clear?
Yes, sir.
Okay. So I will like you to watch this series on scalar triple product. Scalar triple
Yes, sir.
product gives you the volume directly.
Yeah.
So and then we also have one more concept learning about scalar triple product is whether the three vectors are coplanar or not.
Okay.
So I'll give you that concept also. We still have a few minutes here. Okay. Now this is a question for you, right? Can you please read the question and answer?
Yes, sir. It's a true or false question that states if scalar triple product A cross B dot C between three non-zero vectors A, B, and C is 0, then the vectors are coplanar. Explain your answer.
Right. True or false? Explain your answer. So A cross B dot C.
Yeah.
If the scalar triple product, if I get the answer as 0 of this, in that case, we are saying the three vectors are coplanar. Now, what is the meaning of coplanar? All are in the same plane, right?
Same plane. Yeah.
So, if I do dot product between orthogonal or perpendicular vectors, what should I get? 0, right?
0, right. Because
If
close
I
of
have the
90.
same plane, let's say this is the plane of the screen. In that case, I know that the cross product of, let's say, A and B will be the work coming out, right? Do you see?
Coming out. Right.
And since it is at right angles to the third one, the dot product should be 0 because cos
0.
of 90 degrees is 0, correct?
0. Yeah.
So that means the three vectors are in the same plane, correct?
Correct.
So this is a very good proof. If you have to prove that these three vectors are coplanar, what do? You find scalar triple product.
Yeah.
You get the idea.
Yes, sir. Got it.
So I like you to also watch some videos from this particular playlist. Let me share with you the link. Now this is a bit long. It seems it has some good questions in it. So
Yeah.
we are also talking about many concepts while teaching you scalar triple product.
Yeah.
So your teachers might take up scalar triple product soon, but
Yeah.
it is important to be ahead of it. Sometimes they will miss it, right? So we
Right.
can actually look into the properties of being coplanar vectors, as I just said, right? Three vectors are coplanar if scalar triple product is 0.
0.
Linear combination strategies, scalar triple product, and multiple and sub. So this is a big video, which is going to uh, teach you many concepts about the chapter which you are learning. You get the idea?
Yes, sir.
So this is a very important question, video. I
Yeah.
like you to go through this video, understand all the 4 topics.
Yeah.
So the multiple choice test questions will help you review what you have learned so far. So like this, there are many questions. Okay?
Yes, sir.
So I'm just going to stop sharing. So and chat, I'm putting the link. This particular video in between, which we picked, will be of use to you. Let me see.
Yes.
Related. Correct. Now, We talked about scalar triple product, and we figured out how do we find the volume, right? Now, my
Right.
question to you is, how will you find the area of a parallelogram?
Right. So, sir, when we did A cross B dot B, right? Sorry, dot C, then our A cross B actually gave us the height in that case, right?
Okay, area of the base. Yeah, okay, you can say that. Yeah.
So then,
A
sir, in this case,
let's
yeah,
understand A cross B now.
yeah,
So when we did A, B, C, let me just draw anything here, right? Let's say this
yeah,
is A, this is B, right? When you did A cross B, in that case, actually, you got a direction. You A cross B is actually this. Is the area of the base, but the direction is perpendicular.
yeah,
This A cross B. You understand A cross B?
yes, sir.
So we are saying cross product gives us the direction, but the magnitude is equal to the area of the base.
Right.
You get the idea?
Yes, sir.
And to find the volume, we know this is at right angles of the third vector, right? So third
Yeah,
vector times right angle will give me dot product, right?
yeah,
Will give me the volume.
right. Because that's the height, right?
That's the height. So now, what do you need to do? No, that becomes the projection actually. So we have the direction. So when you dot product with this, then so this becomes the projection or the height. That dot product is the height
Oh, okay, okay. Yeah,
because that dot product is actually the projection of C on in this direction.
right. Yeah,
So therefore, it is the altitude of a parallelepiped. You get the idea.
yeah,
So that is the concept. Now, let's get back to, let's say I need two vectors, right? So let's say the vector A is equals to, let's say 1, 2, 3, right? And
yeah,
vector B is, let us say, 2, 0. I'm purposely putting 0, easy calculation, right?
yeah.
Now, if I have to find the area between these two vectors, how will I find the area? Tell me.
Sir, we can do A cross B, right? To find the area.
Magnitude of A cross B.
Right, magnitude of A cross B.
You get the answer. You get the idea?
Yeah,
The magnitude of A cross B, tell me what is the answer. You do any method, right?
yeah. IGQ.
Say I times 2 times 1 minus 0 minus
Yeah,
j. 1 times 1
minus 6.
minus 6, right? Plus k.
Yeah,
And these are unit vectors, right?
correct.
K. 1 times 0, 0, 2 times 2 minus 4. Is it okay? So which is 2i, and this is minus 5j, and this is minus 4.
Minus 4K.
And we have to find the magnitude, area, right? So
Yeah,
which is square root of 2 square plus 5 square plus 4 square. 4 plus 25 plus 16.
yeah,
45, right? 45, right? 45 is 9 times 5, 3 square root 5. Is it okay?
yes, sir.
Unit square. That is how you are going to find the area between in the triangle. Oh, yeah. Now your question is area of a triangle given ABCD, right? Yeah.
Yeah,
This is the area means parallelogram. Okay.
right.
This is area. This is my one vector. This is the other vector. What area I found? I found this area. You understand?
Yeah,
But in your case, in your example, let us say we have a triangle ABC, right?
yes, sir.
Let's say this is 0, 0. Let's make it simple, right? Whatever. See, in this case, you find the two vectors, let's say vector AB and vector AC, correct?
Yeah,
You do cross product of AB with AC,
okay.
half of it Because the cross product will give you parallelogram. Do you see?
Right, and then half it to get the other. Right.
So that gives you area of triangle.
Yes, sir. But if it's just a parallelogram, then we don't have to have it, right?
Yeah. Parallelogram area. So the cross
Yeah.
actually gives you the magnitude, gives you the area, right?
Right.
In the plane in which the two vectors are there, the direction is orthogonal to it, perpendicular to it.
Yeah.
Right? So that is it. So that is how we kind of find the area of a triangle. So that is how you'll answer the other question based on area.
Yeah.
So now with that, we covered not only, so we now know what? Scalar projection.
Yeah. Vector projection. Direction cosine.
And
scalar triple product.
yeah. Area, volume, and scalar triple product, and is very good application is coplanar vector.
Right.
So you can actually find whether the vectors are orthogonal or not, right?
You can. Yeah.
Even
Right.
with product, coplanar in three vectors with scalar triple product, correct? If a
Correct.
scalar triple product is 0, that means height is 0, right? Everything is in the same plane.
Right. Right.
Makes sense, right? Otherwise, so cross product will give me orthogonal vector.
Yeah.
If it is coplanar, in that case, that will be 90 degrees. So dot product will be 0.
0.
So that is how we explain this concept. And actually from here, if they are in the same plane, then you can write one vector as a combination of other two.
Right. The linear combination.
Spanning, which will be the next topic.
Yeah.
How do we span or linear combination?
Yeah.
So that will be our next lesson. How do we span vectors and how do we do linear combination of vectors? Is that okay?
Yes, sir.
So I think a lot of concepts you learned today.
Yeah.
So that brings us into class. So tell me, do you feel comfortable with this topic?
Yes, sir. 100%. It's much more clear now.
Correct. So we did solve many questions from your book within 5 minutes.
Yeah.
With the same speed, you can actually answer the rest of the questions from the coming 2 chapters.
Right.
We'll look into more topics of vectors. Okay?
Yes, sir.
Okay, then. All the best.
Thank you, sir.
Thank you. Bye.
Have a great day.
You too.